Happy Monday, everybody. Happy Monday, the 18th. I have some good news. I finished assessing coursework 1 within the 2-week goal. And the average was way too high on assignment 1. It's the highest average I've ever seen. But it is consistent with my psychic reading that I took about a month ago on the class. So I have according to Blackboard, the average is a 79. The median is an 87. That is crazy ridiculous. But there were people that didn't submit assignment 1 either, so those numbers do not include people who didn't submit assignment 1 at all. So that's pretty crazy. I have the assessment sheets here, and I'll hand them back near the end of class, because otherwise you'll just be flipping through it the whole time, and you won't get to see the slides very well. Also, about the test, I've started writing the test. And you're probably all interested in the test, maybe. I've done a rethinking on the test because if you look at previous tests, has anybody looked at previous tests already for this module? You probably haven't gotten that far yet. You have? Oh, wow. Okay. So previous tests were kind of divided into different topics. One was called introductory topics, one was called info-based topics, one was called volume-based topics, and one was called flow-based topics. And the consequence of that was that a lot of people just ignored the flow-based stuff. They just said, oh, I don't really need to learn the flow-based stuff because it's to answer 2 questions out of 3 exam. So people would just say, okay, I'm going to leave out the flow-based and focus on everything else. And I just thought that was a sad strategy. It makes me cry. So it's not going to be organized that way anymore. There's going to be some flow-based in all of the questions. It's not organized by those topics anymore. For example, I'll give you a hint since you're all here and very enthusiastic. The first question is on pipelines. So you can find pipelines anywhere in the topics. And the second one is called algorithms. So you can find algorithms anywhere, data visualization algorithms anywhere in the module. So it's not a good strategy to just skip the flow-based stuff anymore. I have to mix up the exam too. I have to make it a little bit challenging because the scores are too high. Like I'm just, you're not getting challenged enough. I'm insulting your intelligence. Yeah. Did anybody feel like their intelligence was insulted on assignment 1?
Is the first form still the same?
Yes, it's answer 2 out of 3. Pick 2. Any questions on anything? Doesn't even have to be data viz. I can answer other questions, psychic reading exercises, like anything. If I pick up any questions, I will let you know what the psychic signals. I'm listening for signals right now, actually. The signal I'm picking up now is not a question. The signal I'm picking up now is kind of like, yay, I did well on assignment 1. That's the signal I'm picking up. Okay. So today we're going to talk about flow viz. We're going to do an introduction to flow visualization. Remember we had these three major sub-themes in this, what is the multiple personality disorder again? It's a multiple personality disorder module, schizophrenic data visualization course. It's got info viz, it's got vol viz, and flow viz. And vol viz and flow viz fall under scientific visualization. And that's kind of an unusual configuration. Most data visualization classes are split, either focusing on info viz or scientific viz. But you guys get the full variety of the three topics. Maybe someday we'll split it into two and have like one info viz module and one sci viz module. Would be a fun split. There are some universities that have just a special medical visualization module. I went to a university that had medical viz part 1 and medical viz part 2. Even so. This is an image or a short animation. That's real flow. That's real flow visualization, so to speak. So that is a block on the left, and you can see the flow is being pushed from left to right. And then it's constrained to a thin layer of liquid. It's very thin, only a few millimeters thick. And there's a special light being projected on there. There's a substance that reflects light in the flow, and then there's a special light that's shown on the flow to make the behavior visible. Now, if I ask you a test question, like can you draw that flow, that would be tricky. It's difficult to see. It's complicated behavior. It's difficult to see what's going on there. So it's very helpful to use flow visualization techniques to study that flow. Because a lot of people spend a lot of money looking at real flow like this. And you can go to conferences on real flow, and that's what they do. But it's very difficult. It's to everybody's benefit to use data visualization and specifically flow visualization techniques to study that behavior. It's pretty cool though, isn't it? So let's have an introduction. And if there are any questions or comments along the way, please interrupt. So we're going to talk about flow viz data, different sources of flow viz data, and different dimensionalities of flow viz. And an example, by the way, as well. So a good starting point is just what is flow viz. Right? This is one of the classic sub-themes in the field of scientific viz. And remember, does anybody happen to remember what scientific visualization is? Might be a good refresher. I know that there are some bright people in this class that know the answer to that question, but are afraid to say something. Anybody feeling courageous? Scientific visualization. Scientific visualization is data visualization applied to natural phenomena, or phenomena, you could say phenomena occurring in nature. And the data has an inherent geometry generally. So nature has, well, at least one side of nature has an inherent geometry. So this is the depiction of vector quantities as opposed to scalar quantities. So in the volume visualization part of the module, we were really concerned about scalar quantities or magnitude only. For example, density values, right? About a volume of density values. There's just one scalar per data sample. Here we're talking about vector quantities. So that means every data sample has a location and a direction. Right? A vector is composed of 2 or 3 components. And we see this all over the place in automotive engine simulation, aerodynamics, turbo machinery design, meteorology, oceanography, medical visualization. So it is anywhere you see air or fluid moving, not only, well, air and fluid generally speaking, or gas and fluid. So this field brings special challenges with it. So we want to effectively visualize the magnitude and direction of the data. Previously, we only concentrated on the magnitude. That's a scalar value. And the direction. Now we're including direction. This is the new aspect. Like, which direction are things moving in? And how do we depict that? The data sets are large. They're automatically going to be 2 or 3 times larger than a standard volume viz data set, because every vector has 2 or 3 components. There's 2 components in 2D and 3 components in 3D. It's usually time dependent, so it's usually changing over time. And then we still have this question, which subset of the flow should we visualize? This is a big question because we cannot see all of it at the same time. And in that animation that we just saw, that was a subset of the flow. Whoever set that experiment up confined the flow to a very small, thin volume instead of a big fish tank of volume. You wouldn't be able to see very well if it was a thick tank with all those reflective substances moving along. And in the volume visualization part of the module, we selected subsets of the volume using ISO values and transfer functions. This is how we selected subsets of the volume. You can still do that in FlowViz, by the way. You can still do that if you concentrate on the magnitude of the flow only. But that's generally not what we do if we want to look at the features of the flow or the flow behavior. We generally add other techniques designed specifically to show direction and motion, that sort of thing. So here's just an example. This is some flow. It's actually from an engine simulation. This is actually an intake port, and this is a combustion chamber in an engine. There's a piston head here that you can't see. But the flow comes in, it's let in by the intake port. You could call it petrol if you're in the UK. You guys like petrol, you like to use petrol. It comes in, there's a spark plug. I don't know, has anybody here heard of a spark plug before? It ignites the petrol, causes an explosion, and then that explosion, it changes from chemical potential energy into kinetic energy, which is your pistons. The piston head pushes the piston head down, and that moves your car. We could have a little lecture in just car mechanics or engine mechanics. But anyways, this is concentrating. This is flow magnitude only. We can't see the direction of the flow here. It's just not possible. If I said, please draw which direction the flow is going, you couldn't do it unless you had already studied this process. This is orientation only. It should say really orientation only. So here's that same idea. There's the block, and flow is coming in from left to right. and we're looking at the orientation of the flow. And that's what this looks like. So there's nothing about the speed here. All the speed looks uniform in the right image. Here, there's different speeds. Speed is mapped to color. So dark color, dark red is fast. So here it's fast. Dark blue is slow in that image. That's slow flow. So the question is, one of the questions is, how do we visualize magnitude and direction at the same time? This, by the way, is volume viz. This is volume visualization. Anybody recognize that? Even though we're in a flow viz lecture, this is a slice. And slicing was one of the volume viz methods. So it's just slicing through the flow and visualizing the magnitude. So it's the same as, it's a vol viz technique. This is a flow viz technique. Now, flow viz can be subdivided into different areas. One's called direct flow visualization, and that's when we try to reduce the amount of computation between the flow data and the visual mapping itself. So, for example, just color mapping the flow magnitude. That's a direct flow viz. Or attaching arrowglyphs onto every vector in the flow. That's reducing the computation between the time we input the data and we attach visual mappings to that data. Then we have texture-based flow visualization. This covers the whole flow with typically a noisy texture, and then smears the texture in the direction of the flow. And that's what we just saw. That was a texture. This is a texture-based flow viz. Anybody remember what that thing is there? What that object is? Because I think we saw it once already. I think we saw it in like the focus and context lecture. Anybody remember what that funny looking object is? I see the days of motor heads are gone. That's my impression. And that's a cooling jacket in your motor. All your automotive engines need a cooling jacket to keep the engine from exploding. Well, seizing is the other word. It's to keep the engine from overheating, like a car engine. Which is really, it's kind of sad, because actually all that petrol energy that's stored is lost. It's wasted away to heat and noise. So 80% of that energy is just completely wasted to heat and noise. It's not even used for any useful purpose, which is really shocking. If you didn't know that, then you know that now you know your automotive engine only has 20% efficiency, and 80% of it is just thrown away for nothing. Anyways, I digress. The third category is called geometric. A discrete object whose geometry reflects flow characteristics, for example, streamlines. This is an example of a geometric flow visualization technique. That is a thin surface, and it's everywhere tangent to the flow. It's showing how the flow moves through the cooling jacket. And then we have feature-based techniques. So feature-based techniques have this special property that they perform a search. They search the flow, look for interesting subsets, and then just show those subsets. That's the characteristic. This is an example of a flow, a feature-based flow viz, and those are called vortex core lines. So those are axes around which flow swirls. Where does flow data come from? You're not used to dealing with flow data. Well, actually, you know the answer to this question a little bit because Sally and Betty are flow data actually. But when we build airplanes in software before we do that in hardware. The same with cars and all vehicles that are moving, ships and boats and any engineering. Weather simulation and weather forecasts like the Met Office generate a lot of flow data. Medical data can be flow data, like blood flow, for example. Simulation data. There's a special area of engineering called computational fluid dynamics. Anybody heard of that here? There must be people in here that know people studying engineering, because engineering is a big, I think is it the biggest college here? It might be. It's either that or medicine. But I think engineering, it certainly was the biggest for a very long time, most of the history of the university. But we can also measure flow, like that animation we saw at the beginning was somebody attempting to measure the speed of flow using lighting and techniques and optical measurement techniques, right? So we can set up experimental equipment like tanks using lasers and different fancy equipment that actually literally measures the speed of the flow. And then flow models. So differential equation systems, that is Sally, by the way. Sally is a flow model. Vectors are provided by an analytical formula, that is Sally. You input the x, y, and z coordinates in a time step, and you get back a vector. That's Sally. This is one slide on computational fluid dynamics. This is a degree unto itself. I'm summarizing a degree in one slide. I'm trying to. So if you enroll in engineering here, you can study computational fluid dynamics. Anybody know anybody studying that? And what is that? That it's funny because the whole, you can be, choose this as a career path, and your whole career is generating flow data. Your entire career is just generating flow data. Can you imagine that? That's the way I see it, at least. They probably don't see it that way. So it's the discipline of predicting flow behavior quantitatively. That means numerically, like using numbers. And CFD engineers generate lots and lots of numbers, gigabytes, terabytes of numbers. And then they need ways to look at those numbers, to visualize those numbers. And the data is usually the result of a simulation, the simulation of flow around an object of interest. So the idea is to try to quantitatively derive a method to predict how flow is going to behave when it interacts with an object. That's kind of difficult to imagine, it's difficult to understand, but a typical experiment in engineering, and I think, well, this used to be a setup in the Singleton campus. I don't know about this campus because I'm new to this campus, and I guess so is everybody else here. But like, did anybody ever see the wind tunnel in the old campus? That's a very kind of classic setup. You put an object like a plane inside of a wind tunnel, and then you try to understand how the wind interacts with the surface of the plane. Anyways, there must be something like that here on this campus. But in the old campus, you could walk by the experimental setup in the Talbot building. Like you could just walk by accident, you know. I guess you wouldn't do that here, maybe, with this new setup. Anyway, all the data that we study generally comes from computational fluid dynamics. This is a major source of flow data, and this is the source of Betty. Betty is a CFD simulation. So CFD simulations usually result in large, often gigabytes or terabytes of data. They're usually steady, unsteady. So Betty is a steady flow, by the way. And they often are given on unstructured or adaptive resolution grids. We're not going to get into that in this module. Betty is a structured grid. And the data is usually very smooth. In other words, it doesn't contain very sharp transitions. It's all smooth transitions. These are two images. So this is the simulation image here. That's a CFD simulation trying to study how flow interacts with the surface of a jet plane. And this is the equivalent of a real experiment. So these are two worlds. This is the world. These are both worlds of engineering, but this is computational engineering, and this is experimental engineering. It's two different kind of engineering worlds. But the goal of the simulation is to predict how the fluid is going to interact with the surface in reality. That's the goal. Here are some more examples. These are all different flow visualization examples. Flow past a jet, flow behind a car, flow interacting with the surface, some terrain. This is flow inside a Gulf Stream. These are more flow is examples. This is the one we saw at the beginning. This is the same thing using vector glyphs to visualize that flow. This is using light. This is experimental flow using light. That's using vector glyphs that are not very nice. This is a shock wave, by the way, visualization of shock wave. This is a dynamical system, some dynamical systems. Those are analytical systems. We are having different spatial dimensionality. This is not too shocking, right? So we have flow that's confined to 2D spaces, planes. We often say 2.5D for surfaces, flow confined to surfaces, and we have volumetric flow. That's not too surprising. This is an example of flow confined to a 2D plane. This is flow confined, or the flow viz part, confined to a surface, a texture-based surface. And this is 3D flow. So there's flow coming from the bottom. This is like a kind of hemisphere. And then we see what's happening to the flow after it passes this kind of hemispherical shape. We have steady state flow. That is flow that does not change its behavior over time. Instantaneous flow is another way of saying it. You can use the analogy of taking a photograph for instantaneous or steady state flow. If you take a photograph, you see data, and it's not changing over time. There's unsteady flow, so that's changing over time. That's like getting out your video camera and taking a series of photos, right? 25 frames per second or something like that. That's time-dependent imagery. Not too surprising. I think that's stuff that you all basically know. this is really just a fun slide. It's just giving some example data set sizes, flow visualization data set sizes, in terms of the grids used to simulate the flow and the resulting data set size, but they're associated with years. Like these data sets are now older than you guys, like 1989. So that's a flow simulation data set. In the 1989, a bigger flow viz data set was 13 megabytes. Now you get your like WhatsApp kind of video that's 13 megabytes in size. But look at how quickly the size is increasing over time. So in 10 years, that is 1,000-fold increase-ish, or at least 1,000-fold increase in size. So that's 4 gigabytes in 1999. So it's quickly increasing in size. These are some examples of flow simulations and the resulting data set sizes. Here are some more. Now this is time-dependent flow. The previous example was steady-state flow. And these are ones that you see very often. And so this is a big data set size already, 600 megabytes. And those are some images. This is, by the way, this is an example from 1996, and it's a kind of I don't even know what kind of flying vehicle that is. If that's, but those are 2 propellers, and they're spinning. That is still very challenging today, by the way. That is still an unsolved problem today in 2019. So you don't find this very often, a CFD simulation with moving propellers. It's still a challenge today. We mentioned these 2 categories of direct versus geometric flow viz. So direct flow visualization is very good at providing an overview of the flow, especially steady-state flow. Using vectors is very popular. Vectors attached to every data sample. And geometric flow viz, by the way, geometric flow viz, is this starting to ring a bell for anybody? We have direct flow visualization. What's the complement of direct? I know that some of you are having a psychic moment right now. Where are those attendance sheets? Everybody saw them? What's a complementary word or the dual to direct? Luke, are you feeling psychic today? It's because it's Monday. How about indirect? Direct, does that sound familiar? Oh, I think I'm remembering something. Direct versus indirect. Anyone? Bueller?
Is it indirect when you interpolate the data?
Yes. What's your name? Sam. Awesome, Sam. Sam is going to kick butt in the exam. That's my psychic prediction. So we had this direct versus indirect volume visualization. Here it's analogous. We have direct and indirect. You could say indirect flow viz here. Here it says direct versus geometric. But really you could also say direct versus indirect. One is, if you attach a glyph onto a vector sample, you're visualizing that sample directly. There's no intermediate representation. But if we use geometric flow viz techniques, we are visualizing the flow indirectly. You could say that because you have to interpolate the data samples and look at the interpolated samples to generate those objects like streamlines and stream surfaces. Oh, I forgot, I even say it right here, so it's there. You could have saw that, but sometimes I don't even see my own slides. But anyways, we're going to talk about obviously all these things in detail. So we have two images, one's direct, one's indirect, so to speak, or geometric. This is glyphs visualizing the flow, so you can see a glyph is attached to the samples and it points in the direction of each of the individual vectors. And this is the same data set on the left and the right, but look, using two very different visualization approaches. Anybody want to guess what these are? Any guesses? Those are, you could say those are streamlines, but you could also say they're stream ribbons because they look like they have a width. A streamline wouldn't have any width necessarily, or a very thin width. So same data set, two very different visualization techniques, and you see different things depending on which visualization method you choose. Can anybody think of some advantages or disadvantages if you had to? This could be a good test question, like compare and contrast these two different flow-viz techniques and their advantages and disadvantages. Everybody sign the attendance register? Anybody want to try to answer that one? Name?
Alex.
Alex.
The left image is really busy, so you really can't get anything of detail out of it, whereas the right image kind of clarifies down the important things.
That's correct. That's correct. So this one is busy. The words we use in visualization are kind of, well, occluded. This one has more occlusion than this one, this image. So it's harder to see inside the volume. It's busier. That's one way of saying it. Another way of saying it is this one has less visual coherency. That's another way of saying it. It's hard. However, you can say as an advantage, this one provides an overview of the flow. It's not easy to see. But if I took this and I started to rotate it, then suddenly it would come alive and you'd be able to see a little more about what's going on in there.
Yes, this is a case of focus and context.
Yeah, focus and context would work great here. It would work really well. And we've seen some examples of that, and we will continue to see some. This one also has the advantage in that you don't have to think. Because you don't have to think about where to place the glyphs. They're just everywhere. They're like on a regular grid. This one has advantages in that it provides less occlusion, more visual coherency, because there's an attachment. The flow is behavior. We can follow the behavior of the flow, but we have to think here because we have to place these objects in space somehow. We have to figure out a way to do that. So they both have advantages and disadvantages. Here's a fun application. So the air behind plane spirals, the wingtip vortices example. So when a plane is flying, especially liftoff and landing, it creates vortices behind the wings. Right? I'm sure you all noticed that already. And if another plane is trailing that plane, a given plane, and flies into the vortices, then you can have big problems. Right, the vortices, so another plane coming here might get rotated, so to speak, so there's a down wash, so to speak, and an upwash. And that's one of the reasons why the spacing between the planes has to be carefully maintained. Right, so a big plane is going to create longer trailing vortices, so the distance between the big plane and the two big planes has to be greater, right? The trailing vortices are greater, and the smaller the plane, the smaller the trailing vortices. And a lot of effort goes into optimizing the lift of wings and wingtips. You can imagine this is one of the central objectives for aerodynamic plane design. This is the assignment 1 feedback sheets. They are stacked in conveniently reverse alphabetical order by surname. So this is a kind of visualization of those wingtip vortices. There's a plane, and those are regular slices. Visualizing the perpendicular flow, the flow perpendicular to the vortices, and then there are these lines that are not very high quality, but those are vortex core lines, so the axes around which the flow swirls. There's a close-up view that's higher quality so you can see it. And so somebody has taken 2 slices through the flow and then projected the flow onto the slices, and we can see where the swirling flow behavior is and the vortex core lines. So those are 2 techniques being combined. The direct flow viz, which is the color-coded slices, and then the feature-based flow viz, which is the vortex core line extraction. And there are some more images of the same thing. But those are you can see the viewpoint looking head-on into the plane. That's the time, so like the earliest time step, another time step later, and another time step later. So you can see how the magnitude of the vortex is decreasing with time, and the position is decreasing as well. Okay, let's look at some demo videos. I don't remember which one is which. I think that's the same as that one. Here's a fun. I think if this is the one I think it is, it's quite a fun one. So this is trying to visualize the flow, real flow in a real experimental setup. And you can imagine that is one expensive experiment. That is not going to be a cheap setup, right? Anybody here ever try to rent a plane before? Like, usually you don't because it's too expensive. Right? There aren't many people that can rent a plane. But this is a rented, well, I don't know if this is a rented plane. I'm guessing it's a rented plane, but I don't really know that. And it's not only a rented plane, but it's a pimped up rented plane, like attached with a lot of special equipment to create smoke. That's what's happening. We're trying to create smoke and light using lighting and smoke effects to visualize those vortices behind the wingtips. So those are the vortices behind the wingtips. And that's trying to understand their behavior in real life, right? And see, so people study this in real life and using computational fluid dynamics. But the idea is that a real experiment is very expensive. It's expensive to rent a plane, pimp it up, fly it. But guess what? It's not just one plane. It's two, because there's a plane filming, or there's something filming this plane. Could be another plane. Right? So it's renting two. And that's one expensive experiment. I don't know how much that experiment costs. I have no idea. Maybe 100,000 pounds, maybe something like that. I really don't know. But it's going to take some very special expertise. So it's so expensive. That's the whole motivation behind computational fluid dynamics and simulation. The goal of computational fluid dynamics and simulation is to perform the same experiments in software and get them as accurate as possible to lower the costs, because it's cheaper to do these things, not always, but it should be, or we try to make it as cheap as possible to do these experiments in software before doing them in hardware, because the hardware versions are so expensive. So it's cheaper to model a plane, simulate the flow moving past the plane in software than it is in hardware, or in virtual reality, you could say, versus reality. So that is the goal. That's the whole business like going on in engineering over there, right? That's what they're all studying. And the simulation, if anybody happens to be interested, the simulation is that discipline is what got Swansea University really on the map, on the global map. So one of the founders and creators of CFD simulation was a professor at Swansea University. And that's why the university has such a history. Okay, I guess we'll stop there. Any questions?